Hi guys, good evening. We are Team 203 and this is our Checkpoint 3 presentation. Our team members are Tristan, Aaron, Savani, and Emmy.
So here you can see the final concept drawing for the proximity tentacle. In the top left, you can see the motor assembly, which would pull on the string, making the arm contract, which loads the springs, essentially the rubber bands, with an elastic force. And the idea was that then, after a short period of time, the motor would relax and the arm would return to its natural state. So that was the idea for the anisotropic response. You can see some details of the joints in the middle. And in the bottom left is how it would have looked if we had gotten a physical prototype built, but due to team dynamics, we weren't actually able to 3D print the joints. And so in the bottom right, you can see the final motion of what would have happened, the idle state, the full retraction, and then the rest motor relaxation.
Hi guys. The block diagram is all about communication in the hardware. In this diagram, we have our power module, our IR sensor module, our temp sensor, and our motor module. The motor module is connected by 4 digital pins that uses SPI communication, and the temp sensor also uses 4 pins that are digital and uses SPI communication as well. Our IR sensor is an analog sensor that uses analog imprints to activate ADC on a PSOC. Our power system powers up the whole board by converting a 9-volt input current to 5 volts. The analog sensor is made from the QED Q23 QSE113 and is a signal condition analog sensor with an op-amp and communicates with the PSOC using ADC.
Here you can see the entire PCB with all 4 subsystems. Starting on the left at RD1 in the top left-hand corner, you can see the voltage divider going down into the op-amp with the pins for the phototransistor and the 880 nanometer diode emitter. In the very bottom left, you can see the 5-volt barrel jack and the fuse, and the small linear voltage regulator. In the middle, you can see the headers for the PSOC, where the actual BLE module is attached to the PCB. In the top right, you can see the 9-volt barrel jack for the motor drive and the motor control. And just below that, you can see the temperature sensor. And throughout the board, there are debugging LEDs to show that we are truly getting 9 volts and 5 volts to the board, and also that we have an output from the PSOC.
Here we have the final hardware schematic. There are 4 total sub-assemblies. Starting with the bottom left is the power supply module, which consists of an AC to DC adapter connected to a barrel jack, which feeds to a voltage regulator, turning 9 volts to a 5-volt DC supply, bringing power to the PSOC. Above that is the IR proximity sensor that uses a diode to emit infrared light and a phototransistor that draws a range of current, which goes to a resistor voltage divider and op-amp that creates a variable voltage between 1 and 5 volts. To the right is a motor assembly, which includes a DC motor driver powering a stepper motor, which is all powered using a 9-volt wall plug. This subsystem relies on a signal produced from the IR sensor to actuate the motor. Below that is a temperature sensor. This works alongside the motor assembly and is powered directly by the PSOC. The sensor detects if the motor assembly temperature is above normal operational range, and if so, sends a serial signal stopping motor actuation.
For the process of completing our final code, our team needed to utilize both SPI and analog communications methods. The SPI portion would activate the motors and is controlled using an SCB hub on the top design, allowing for all the MOSI, SOK, and other SPI-specific pins to function. Our analog sensor would be an IR sensor and is ran off a UART and ADC communication block, allowing for the proper distance to be read. Reviewing the code itself, we begin with the IR sensor, which allows us to take in a voltage reading and convert it to a distance using the UART and ADC commands. From this distance, we activate our motors. How this works is if there is no object within range of the IR sensor, the motor does not move, and then once an object comes within range, the motor is allowed to move, moving the arm overall.